Hello, my name is John Kariuki, and I'm a cloud software development engineer at Intel, who collaborates with Intel customers to build high performance, scalable storage solutions using open source software such as the Storage Performance Development Kit, also known as SPDK. In this talk, what I'm going to be talking about is I will be talking about the work that the SPDK community has done to provide strong error detection for the NVMe over TCP protocol data units with hardware accelerators such as the Intel Data Streaming Accelerator, also known as DSA. So here are the notices and disclaimer, and this talk does actually contain performance data that is based on the configuration that I used to collect the data, and I've provided that configuration information in the backup slides. So if you want to get a detailed view of the configuration that I use for performance benchmarking, take a look at the slides in the backup. So first things first, I'm going to go over a quick introduction of the work that was done, and then I'll share the setup that I used for benchmarking. And then later we're going to look at some performance data. In NVMe over TCP, a host and a controller communicate over TCP by exchanging NVMe over TCP protocol data units. These PDUs are used to transfer capsules, they transfer data, they transfer control and status information. As I'm showing here on the diagram here to the right, these PDUs can have up to 5 fields. There is an optional field in these PDUs that is called the data digest field, and that's that last field there that's labeled DDGST. That field may be included or it may be omitted based on the PDU type and the values that are exchanged during the establishment of a connection. If that data digest is enabled, the digest field, if the data digest is enabled, the data digest is contained in that field, and it's used to protect the PDU data field above it. And the way the data digest is calculated, that's done using the CRC32C algorithm that's defined in RFC 3385. And that's because the CRC32C algorithm provides strong error detections on communication network. And there's also been support for instructions in the CPU that can accelerate this computation. And that's been available going all the way back to SSC 4.2. There's also libraries out there like ISA-L that provide highly optimized implementations of the CRC32C algorithm. So this algorithm is well known, and there are a lot of really efficient implementations out there that can be used to perform this the CRC32 calculation efficiently. So next, let's take a look at the hardware and the software components in the test environment that I use for benchmarking. So we're going to look at how we set things up on the target first. So we're running the SPDK NVMe over TCP target application, and that's running on a system that has the 4th generation Intel Xeon Scalable processors that are codenamed Sapphire Rapids. The system it's a 2-socket system, and each CPU has one DSA device. That system also has 16 NVMe SSDs, and those are evenly split between the 2 sockets. So we have 8 SSDs on one socket and 8 SSDs on the other socket. So as far as the networking goes, the target system connects to two initiator systems over two 200 gigabit per second NICs. And these are the Intel EA10 NICs, and they're set up in the target system such that we have one 200 gig Intel EA10 NIC per socket. And then moving on over to the initiator side, we're running FIO, and we're running it in server mode. That way we can submit IO requests from both initiator systems concurrently at the same time to the target system. So if we look at the IO path, right, the path that an IO request follows in this setup, it starts on the initiator side with FIO sending IO requests to read data from an NVMe subsystem that resides on the target system. When the target receives those requests to read data from these NVMe devices, it goes out and submits a request to the device, reads the data, and then if we have the data digest enabled on the target side, the target uses the SPDK acceleration framework component to compute the data digest. The acceleration framework is an abstraction that the SPDK community has developed over hardware accelerators that comes with the software plugins that can be used in environments where these hardware accelerators do not exist to perform the functions that are being offloaded to these hardware accelerators. And if you would like to learn more about the SPDK acceleration framework, Paul Lewis is doing a talk about the acceleration framework, so I would encourage you to listen to that talk. The acceleration framework in our setup uses one of two methods to compute the data digest. On a system that has the Intel DSA engine, the target can offload the CRC32C computation to the DSA device. And on systems that don't have hardware accelerators, the target uses ISA-L, which is the Intelligent Storage Acceleration Library, to compute the CRC32C digest on the CPU core where the application is running. With ISA-L, what ISA-L does is it provides a software optimized implementation of the CRC32C algorithm in a library that's actually very widely adopted in the storage industry because it can compute this CRC32C digest very efficiently on the CPU. So finally, once the target has computed the data digest, it takes the digest and the data and puts that in a PDU and sends that over to the initiator system. And that's pretty much the data flow. So our test objectives were really to compare the performance and efficiency of offloading the CRC32C computation to the DSA hardware accelerator versus computing that digest on the CPU cores that are assigned to the target application, where it would be competing for CPU cycles with the other work that's being performed by that storage target application. So the way we set up the test is we had 3 test configurations. And in the first configuration, we had the data digest disabled. So there was no CRC32C data digest computation being performed by the target at all. The purpose of this configuration was really to help us understand the CPU overhead of using the DSA engine in the first place. In the second configuration, we had the data digest enabled and the CRC32C was calculated using the ISA-L software. So once again, ISA-L is the Intelligent Storage Acceleration Library. And the ISA-L implementation uses the vector carryless multiplication instructions that are part of the AVX512 instructions in Intel CPUs. What using ISA-L does is it provides a software implementation, a software optimized implementation of the CRC32C algorithm that can be used in systems that don't have DSA. And what this means is that it means that the target application would work, right? It would provide data protection both in environments that have the DSA hardware accelerator and those that don't have the DSA hardware accelerator. And then the third and final configuration, we had the data digest enabled, and we offloaded that CRC32C calculation to the DSA engine on the target system. So we ran the test, and we measured the performance in IOPS. We also measured the CPU utilization, and we calculated the IOPS per core so that we can show the CPU efficiency of each of these test configurations. And to do that, basically what we're going to be doing is we're going to be comparing the performance in IOPS and the efficiency in IOPS per core of these three different test configurations. So now let's jump right in and take a look at some performance data, right? Let's take a look at the performance numbers that we collected for these three configurations. In the first test that we performed, we configured the SPDK target to use just a single CPU core. And then we went over to the two initiator systems that we have connected to this system. And we started submitting I/O requests, and these were I/O read requests to the NVMe subsystems that reside on those NVMe devices that we have on the target. We did this for three different block sizes, and those are 4K and 16K random reads, and 128K sequential reads. And for each of these block sizes, we tested with 4 Q depths, a Q depth of 8, a Q depth of 16, and a Q depth of 32 and 64 per NVMe SSD. So if you remember that we had 16 SSDs on the target system, if you multiply those Q depths that I just mentioned with 16, you will get the Q depths of the target that I'm showing here on this slide, which is a Q depth of 128, 256, 512, and 1024 on the target side. So we measured the IOPS that we were getting on the target when it was using just a single core and calculating the digest using ISA-L. And then we also measured the IOPS that we were getting on the target side when we offloaded that CRC32C computation to DSA. And we also measured the CPU utilization for each of these tests, and that helps us compute the IOPS per core. The data that you're looking at, those percentages, are the comparisons in IOPS per core when offloading that CRC32C calculation to DSA versus doing it using ISA-L on that same CPU core that the target is running, where it's competing for CPU cycles with the rest of the work that the target is doing. And basically, as you can see, what we observed is when the target was CPU bound at the high Q depths, offloading that CRC32C calculation to DSA significantly improves the IOPS per core. We can see that for 16K random reads, the IOPS per core were up to 34% higher when we used DSA, and up to 71% higher for the 128K sequential reads. At low Q depth, the workload is not CPU constrained, and that's because SPDK uses a pull mode design. And what that means is if you give the SPDK target a CPU core, it will use the entire CPU core. So at low Q depth, there were enough CPU cycles for ISA-L software to perform that CRC calculation on the CPU, and also for the target to perform the other tasks such as processing the incoming I/O request via NVMe over TCP, and also submit and complete I/Os to and from the NVMe SSDs. And then for small blocks, right, for the 4K random read blocks, ISA-L software actually performed pretty well, right? For the most part, it was on par with offloading to DSA. So next, we're going to look at the performance and efficiency of offloading that CRC32C digest to DSA as we scaled the number of CPU cores that are used by that target application until the 400 gigabits per second network is saturated. This graph here that I'm showing, it shows the relative IOPS per core for the target application when it was using DSA to compute the digest, and that's that green bar. That's what that green bar is, and it's normalized relative to that blue bar, which is the target using ISA-L to compute the digest. And basically, we measured these numbers as we increased the number of target cores from 1 to 2 to 3, and this is for the 128K sequential read workload at that high Q depth of 1024. We also did one more thing. We also measured the relative IOPS per core when the target didn't even calculate that digest at all, and that's what that yellowish gold bar there is. And basically what we saw is as we give more CPU cores, more CPU cycles to the target was taking advantage of those additional CPU cycles to submit more work to DSA, and hence we see the IOPS per core for the target when it was using DSA, that green bar. We see that coming pretty close to matching the same numbers as when the target wasn't even computing the digest at all. The graph on the right here shows the number of CPU cores that were consumed by the target to saturate that 400 gigabit per second network. And what we observed is that when the target was offloading that CRC32C data digest computation to DSA, it took just 6 cores to saturate the 400 gig network. And this was actually the same number of cores that the target used if you did not calculate that digest at all. So if your workload is one of these large block workloads that is sequential, like the 128K sequential blocks, and you're not doing this, you can do this with DSA for no additional CPU overhead. That's what those the green bar there on that graph on the right and the gold bar telling us. And that's because with DSA, DSA completely eliminates those 3 cores of ISA-L software overhead. So next, we're going to take a look at latency numbers. So we're going to take a look at the relative latency that we measured when we used DSA to compute the data digest versus doing it in on the CPU using ISA-L. And the numbers I'm showing here were collected when the target was configured with 3 CPU cores. But this was a pretty similar pattern that we saw, that whenever the target was running and the workload was CPU bound, we saw a reduction in average latency that was up to 46%, and the P99 latency reduction of up to 34%, and P99.99 latency reduction of up to 31% when we use DSA to calculate digest versus ISA-L. calculating the digest on the same CPU cores that are being used by the target application. So next, let's take a look at the relative IOPS per core performance numbers for the 16K random read workloads. So let's take a look at what happened as we increased the number of CPU cores that were being used by the target for this workload, and we also increased the queue depth at the target side to present more work at the target. So what we saw is as we scaled the workload and the number of CPU cores that were used by the target, is as we are showing here with the green bar, which represents the IOPS per core for the target when it was using DSA to compute the data digest, versus the blue bar, which is when the target used ISA-L to compute the digest, is we measured a 25 to 34% IOPS per core improvement when using DSA versus when using ISA-L to compute the digest. And then looking at the relative IOPS, when we use DSA, that's a green bar versus the gold bar, which is the relative IOPS when we did not even compute the digest in the first place. We can see that as we increase the amount of work that the target is doing and the CPU cores that the target is using, we can see that with DSA, the target is actually closing that performance gap. And as a matter of fact, when we measured the number of CPU cores that it took to saturate that 400 gigabit per second network for this workload, is that we observed that with DSA, it took just 10 cores to saturate the 400 gig network when we offloaded that CRC32 calculation to DSA. And that was actually the same number of CPU cores that it took if the target did not even compute that data digest in the first place. So once again, here we see DSA eliminating all the 4 cores of software overhead that are used by ISA-L to saturate the 400 gig network. And once again, if you're not doing this because it's computationally expensive, right? If you're not computing the data digest because it's computationally expensive in terms of CPU cycles, using DSA will eliminate that software overhead of computing that data digest in CPUs. So next, let's take a look at the latency numbers for the 16K random read workload. So when the workload is CPU bound, we measured an average latency reduction of up to 38% and P99 latency reduction of up to 33% and P99.9 latency reduction of up to 19% when we offload the digest calculation to DSA versus doing it on the CPUs that are assigned to the target application with ISA-L. Next, let's take a look at the relative IOPS per core for the 4K random read workload. So for this workload, ISA-L actually did pretty well. The gap between ISA-L in terms of IOPS per core and offloading to DSA, well, it wasn't that big of a gap. But that said, we still saw anywhere between 8% and 15% more IOPS per core when we offloaded that CRC32C digest calculation to DSA for this workload, as we scaled the number of CPU cores from 1 all the way to 20 cores and saturated the 400 gig network at 11, just under 11 million IOPS. So looking at the graph here on the right, we can see that it took the target 32 cores to saturate the 400 gig network, hitting roughly just under 11 million IOPS with DSA. And that is still a 10% reduction in the CPU cores that were used by the target when it used ISA-L, which is the blue bar. And then as far as the latencies go, for the 4K random read workload, we measured the average latencies reduction of 11%, P99 latency reduction of 9%, and P99.99 latency reduction of 7%, up to 7% when we used DSA to calculate the digest versus doing it with ISA-L on the same CPU cores that were being used by the target application. To summarize the test results of our performance benchmarking, we observed significant gains in IOPS per core for large block workloads. We offloaded the CRC32 digest calculation to DSA versus doing it in software using ISA-L. We start seeing pretty clear gains starting at 16K block sizes. At the 4K block size, ISA-L actually performed pretty well. As we increase the QDepth, right, what we saw is at higher QDepth, there was more work to be submitted to DSA concurrently, and that actually increased the value of offloading the digest calculation to DSA. So QDepth is one of the keys to realizing that benefit of offloading that digest calculation to DSA. And then last but not least, I want to talk about the benchmark that we the baseline that we're comparing against, right? So ISA-L has this highly optimized CRC32 function that takes advantage of the vector instructions, vector AVX instructions that we have in the Intel CPUs. When we actually went in and we compared the performance of the target when it was using ISA-L to do this versus using the CRC32 instruction, we measured over 20% more IOPS with ISA-L versus when the target was using the CRC32 CPU instruction to calculate the digest. So if you are doing the CRC32C computation in software today, and you're not using the latest and greatest version of ISA-L, you might actually get a little bit more mileage than what we said, what we showed you in this presentation. And finally, the SPDK community is building a framework for using hardware accelerators such as DSA and QAT. And that framework is designed for software-defined storage. And what I mean by that is the framework is being built with software plugin modules that can be used in environments where the hardware accelerators are not present. So today, there's already a bunch of functions that are supported by this framework, and there's more coming soon. If you're interested in this work, please join the SPDK community by going to spdk.io/community. Thank you so much for listening to this talk, and please take a moment to rate the talk.